Get ready to get bent, twisted, and compressed, but in a totally professional way. You're listening to Mechanical Engineering Made Simple.
I love that intro. It's very accurate for what we're doing today.
Right. I mean, imagine you're sitting in the cockpit of like a 300-ton Boeing 777.
Oh, wow. Okay, setting the stakes high early.
Exactly. So you're flying directly into the outer bands of a hurricane.
Yeah.
The aircraft is yawing left. It's pitching up, rolling in these massive crosswinds.
That's terrifying, honestly.
Yeah. And your onboard sensors are just screaming data at you. But here's the thing. Your flight computer has to take the wind velocity hitting the nose of the plane and instantly translate it into true wind velocity relative to the Earth down below.
Right. It has to shift reference frames.
Exactly. And if that computer executes a single matrix multiplication in the wrong sequence,
Yeah.
literally, if it calculates A times B instead of B times A,
Oh, yeah. That's a bad day.
it feeds corrupted telemetry to your autopilot, and the plane can quite literally tear itself apart. So today, we are cracking open the invisible code that prevents that from happening.
It's the hidden architecture of reality, really. I mean, it's the math that dictates whether a commercial airliner stays in the sky or, whether a suspension bridge holds up under rush hour traffic.
Exactly. So our source text for this deep dive is a pretty dense foundational document. It's titled 6 Matrix Tensors Dyadic Sand Rotation Operators.pdf.
A very catchy title.
Oh, totally. Rolls right off the tongue. But look, if you've spent any time in engineering or applied physics, you already know we aren't here to relearn basic calculus.
Right. We assume you know what a matrix is.
Yeah, exactly. What we're doing today is taking this intense mathematical scaffolding stuff like Cartesian tensors, dyadics, direction cosines, and translating it into the intuitive key realities they actually represent.
Because it's not just numbers on a page. We want to explore exactly how a specific arrangement of numbers perfectly describes a tumbling rigid body. Or the internal shearing forces of a steel beam.
All right, and I think we should start right where the text does, which is shifting our reference frames.
Yeah, that makes sense. Before we can track that 777 tumbling through the sky, we have to establish how to translate coordinates.
From a fixed reference frame, right?
Yep.
Like the Earth.
Exactly, from the Earth to a moving, rotated reference frame like the aircraft itself.
So the math here relies on linear transformation matrices, specifically rotation matrices that are built out of direction cosines.
Right, which sounds complicated, but it's really just about angles.
Yeah, so if you have your fixed unprimed axes, x, y, and z, and your rotated primed axes, x prime, y prime, z prime.
The new perspective, basically.
Exactly. The relationship between them isn't just arbitrary. It's strictly governed by the cosine of the angle between any new axis and any old axis.
So, for example, the matrix element, a 1, 1.
Right, the top left corner of the matrix.
Yeah. That element is simply the cosine of the angle between the new x prime axis and the old x-axis.
And you just calculate that for all 9 combinations to build your 3x3 transformation matrix, the matrix A.
Exactly. So your new position vector, let's call it x prime, is equal to that matrix A multiplied by your original position vector, x.
But the text quickly pivots from this basic setup to a really critical property of these matrices, orthogonality.
Yes, this is where it gets elegant.
And to explain it, it introduces the Kronecker delta function, which is denoted as delta subscript KL.
Which is a very fancy name for a very simple concept.
I always think of the Kronecker delta like a highly specific VIP bouncer at a club.
Okay, I like where this is going.
So if the two indices don't match exactly, if K is 1 and L is 2, the bouncer says no. It outputs a 0. It completely kills the term.
Right, access denied.
But if they match perfectly, say K is 1 and L is 1, the bouncer lets you in, it outputs a 1.
A logic gate is a really functional way to code it in your head. But physically, what the Kronecker delta represents here is the dot product of orthogonal unit vectors.
Okay, break that down for us.
Well, we are operating in a Cartesian system, right? So our x, y, and z axes are, by definition, 90 degrees apart from each other. They are mutually orthogonal.
They make a perfect corner.
Exactly. So if you take the dot product of the unit vector for x and the unit vector for y, well, the cosine of 90 degrees is 0. They annihilate each other.
Right, because they share no directional component.
But if you take the dot product of x with itself, the angle is 0, and the cosine of 0 is 1. So the Kronecker delta is simply the mathematical enforcement of perpendicularity in our physical space.
Which, and this is the crazy part, leads to a massive computational shortcut.
Oh, a huge one.
Because our axes are orthogonal, the matrix A is an orthogonal matrix.
Mhm.
And the text proves that for an orthogonal matrix, finding the inverse is bypassed entirely.
Yeah, and we should remind people that historically finding a matrix inverse is a nightmare.
Oh, it's terrible. Calculating cofactors, determinants, adjoints, it's like doing long division in Roman numerals.
That is a perfect way to describe it. It's computationally so heavy. But for an orthogonal matrix, the inverse is simply its transpose.
A inverse equals A transpose.
It cannot be overstated how important that is for computational efficiency in, like, real-time software.
So let's look at example 6.1 from the text to see how this plays out physically.
The airplane example.
Yeah. We have an airplane flying horizontally. It has its own local coordinate system, the prime system. And the airplane has yawed.
Meaning it has rotated around its vertical z-axis by some angle, theta.
Right. It's crabbing sideways relative to the fixed Earth coordinate system. And the airplane's onboard sensors measure a wind velocity vector, v prime, in its own yawed reference frame.
But the pilot, or the autopilot, needs to know the true wind velocity, v, relative to the Earth.
Right. So if we just had the equation v prime equals a times v, and we needed to solve for v, we would normally have to multiply both sides by the inverse of a.
Which, as we said, is a Roman numeral nightmare.
But thanks to orthogonality, we know a inverse is just a transpose. So v equals a transpose times v prime.
It's just so clean. You literally take your 3x3 rotation matrix and you swap the rows and columns.
So like the negative sine theta just flips across the main diagonal.
Exactly. You flip it like a pancake and multiply it by the measured velocity.
And the resulting equations just fall out beautifully. The true x velocity on Earth is v prime x times cosine theta minus v prime e times sine theta.
It is clean, it is computationally lightweight, and it is exactly what flight processors are executing thousands of times a second to keep drones and planes from crashing.
But, you know, a yawing airplane is just a single rotation around a single axis. What happens when our rigid body is completely unconstrained, like a satellite tumbling in space?
Then we enter the domain of Euler angles.
Right, because to define a solid body tumbling freely in 3D space, you have 6 degrees of freedom.
Yes, 3 are translational, so the XYZ position of the center of mass, and the other 3 are rotational.
And Euler angles track those rotational degrees of freedom using a strict sequence of 3 angles: phi, theta, and psi.
And sequence is the key word there. The text lays out the classic 3-2-3 sequence, or at least a variation of it.
Okay, let's walk through that sequence. Step 1. First, you rotate the original axis counterclockwise by phi around the z-axis.
Right, and this gives you your single prime coordinate system. The z-axis stays fixed, pointing up, but your x and y-axis sweep across the horizontal plane.
Got it. Then step 2. You rotate by theta around the new x prime axis.
And this is where it gets highly dynamic, because we aren't rotating around the original room's axis anymore. We are rotating around an axis that we just moved.
And that specific tilt, the text says, it introduces what physicists call the line of nodes.
Yes, the line of nodes. It is essentially the intersection of the original fixed xi plane and the new tilted x prime e prime plane of the object. It acts like a hinge for this second rotation.
Okay, so we tilted on the hinge. We are now in the double prime system.
Correct.
Finally, step 3. You rotate by psi around the new z double prime axis, giving us our final triple prime orientation.
And mathematically, what we've done is just chained together 3 distinct rotation matrices: R1, R2, and R3.
So the total orientation is defined by x triple prime equals, parentheses r, 3 times r2 times r1 times x.
Yes, and notice you multiply them from right to left. That represents the sequence of operations applied to the original vector x.
Okay, so this brings up a massive debate in aerospace and robotics, because Euler angles force us into this rigid sequence, right?
They do.
And because matrix multiplication is non-commutative, meaning the order you multiply them fundamentally changes the answer. We run into vulnerabilities.
Very serious vulnerabilities.
Right. If I turn a block left and then tilt it up, it ends up in a completely different position than if I tilt it up and then turn it left.
So if it's so computationally heavy and prone to alignment issues, why do we still teach and use Euler sequences?
I mean, why not just abandon Euler angles entirely and use quaternions?
Exactly.
That is the exact right question to ask, and it really gets to the heart of how engineers choose their mathematical tools. Because quaternions are kind of the modern standard, right?
Yeah, quaternions, which use a 4-dimensional complex number system to describe 3D rotation, they are computationally superior in almost all modern software applications.
They avoid the gimbal lock.
They absolutely avoid the fatal flaw of Euler angles, which is gimbal lock.
And when I hear gimbal lock, I immediately think of the Apollo 11 nightmare scenario.
Oh, it's the classic example. Let's look at Apollo 11 physically. Their inertial measurement unit, the IMU, was essentially a stable platform isolated from the spacecraft's tumbling by three physical motorized rings, the gimbals.
And those gimbals corresponded directly to our Euler angles: roll, pitch, and yaw.
Exactly. The mathematical sequence of rotations physically manifested as nested rings of metal in the spacecraft.
Okay, so what happens when it locks?
Well, imagine you pitched the spacecraft up exactly 90 degrees. In a three-gimbal Euler system, that 90-degree rotation physically aligns the yaw gimbal directly parallel to the roll gimbal.
Oh, you folded two axes of rotation completely on top of each other.
Right. You just lost an entire degree of freedom. If the spacecraft then yaws, the IMU can't track whether it's yawing or rolling. They are the same physical hinge at that point.
So the math divides by zero, the platform spins out of control, and the navigation computer literally loses its orientation in space.
And the Apollo astronauts had to stare at their 8-ball nav ball, absolutely terrified of approaching that 90-degree pitch mark, because the Euler mathematics govern the physical hardware.
That is wild. So back to my question, why use them if they have this fatal flaw?
Because Euler angles are easily interpretable by human beings.
Oh.
When a pilot looks at a dashboard, they need to know pitch, roll, and yaw in degrees. That makes intuitive sense to a human brain.
Right. If you tell a pilot, hey, your quaternion vector is 0.707, 0.7070.
It means absolutely nothing. They can't intuitively land a plane with that. So Euler angles offer physical transparency, even if they have mathematical blind spots.
That makes perfect sense. The math has to interface with the human operator.
Exactly.
But, up to this point, we've really only been talking about rigid bodies. A spacecraft, an airplane, a tumbling block.
Things that don't change shape.
Right. We are just rotating a coordinate frame around a solid object. But what happens when the object isn't perfectly rigid?
Oh, now we're getting into the good stuff.
What happens when we are dealing with a complex web of internal forces? Forces that are stretching and tearing the material in different directions simultaneously. A simple rotation matrix isn't going to cut it, is it?
Not even close. We have to upgrade our math to Cartesian tensors.
Tensors. Just the word sounds intimidating.
It does, but tensors are simply the language of continuum mechanics. Think of it this way. A matrix is just a grid of numbers. But a tensor is a geometric entity that perfectly describes physical properties, regardless of how you rotate your coordinate system.
Okay, so the text categorizes them by rank. Let's walk through these. A rank 0 tensor is a scalar, 0 indices.
Right, things like temperature, mass, energy. It's invariant. If you rotate your reference frame, if you stand on your head, the temperature of the room doesn't change.
Exactly. Then you have a rank 1 tensor. That's a vector. It has one index.
Like velocity or force.
Right. And the text actually proves a really neat concept here. The dot product of two vectors, two rank 1 tensors, yields a rank 0 tensor.
Wait, so multiplying two vectors gives you a scalar?
With a dot product, yes.
Yeah.
And this is a critical proof. The dot product yields a scalar that is invariant under coordinate transformation. It's what we call an isotropic tensor.
Okay, so that's rank 0 and rank 1. Now we step up to rank 2. Two indices.
This is where things get real. Stress, strain, the moment of inertia.
This is a 3x3 matrix in 3D space, requiring 9 components.
Yeah.
Now, I've heard people compare a rank 2 tensor to a spreadsheet, but that feels a little hollow to me.
Yeah, a spreadsheet is just dead data. It doesn't capture the physics.
Exactly. I prefer to think of a rank 2 tensor like a block of Swiss cheese that I am pulling apart with my hands.
I am highly intrigued by the Swiss cheese model. Walk me through it. Okay, so if I have a scalar, rank 0, I just know the cheese has holes. It's a single fact.
Okay, invariant fact. Got it.
If I have a vector, rank 1, I know which way the block of cheese is moving across the table, direction and magnitude.
Right.
But if I want to describe how the cheese physically deforms, how the round holes stretch into ovals, how the cheese squishes on top while it's tearing on the bottom because I am pulling it from 3 different angles with varying amounts of force, I need a rank 2 tensor.
Oh, that is good.
It defines not just a force, but the surface that the specific force is acting upon.
That is a much more robust analogy than a spreadsheet because it captures the multidimensionality. A stress tensor component, say sigma ij, tells you exactly that. The force acting in the j direction applied to the surface whose normal vector points in the I direction.
It is the marriage of a force vector and an area vector.
Exactly. And to construct these rank 2 tensors, the text introduces something called dyadics.
Right, and this is interesting. If you take two vectors, A and B, and you just place them next to each other without taking a dot or a cross product, you get a dyad, AB.
It's an outer product, and we have to stress here, it is highly non-commutative.
Order matters again.
Massively. The text is very explicit about this. A vector C dotted with the dyad AB so, C dot parentheses A, B, produces a vector pointing in the direction of B.
Right.
But parentheses AB dot C produces a vector pointing in the direction of A.
So the order dictates physical reality. That's fascinating. But honestly, here's what I think is the most powerful concept in the tensor section of the text. Contraction.
Oh, yes. Contraction paired with the Einstein summation convention.
Right. So the text talks about taking an equation with a high number of indices, and by setting two indices equal to each other and summing them up, you reduce the rank of the tensor by 2.
It steps down. It drops from a rank 4 to a rank 2 or rank 2 down to a rank 0.
But why is contraction so powerful in physics? What does it actually do for us?
Because it is how we discover the fundamental unchanging truths of a system. When you perform a contraction on a tensor, say, summing the diagonal elements of a rank 2 stress tensor, which gives you TII, you are calculating the trace of that matrix.
And the trace is an invariant.
Precisely. You are essentially projecting this complex multidimensional state space down into a lower dimensionality. You strip away all the noise of the coordinate system.
The rotation doesn't matter anymore.
Right. When you sum over repeated indices, you are calculating the parts of the tensor that perfectly oppose or align with each other. It takes that chaotic pulling and stretching Swiss cheese and distills it into a single invariant physical law.
Like volumetric expansion.
Exactly. A law that remains true no matter how you look at the object.
That reduction of dimensionality is just beautiful, and it perfectly sets up our next major application. Because we're going to take this rank 2 tensor and apply it to a deeply physical problem, rotational mass.
Inertia.
Yes. So we know that in linear dynamics, force equals mass times acceleration. And mass is a simple scalar, a rank 0 tensor.
Right. But if you try to spin an object, a scalar mass is totally useless.
Because the effort it takes to spin a flywheel depends entirely on where the mass is located relative to the axis of rotation, right?
Exactly. Which is why we need the inertia tensor I sub m.
And the text derives this by examining the angular momentum L of a rigid body comprised of point masses.
Right, and it yields the equation L equals I sub m dotted with omega, where omega is the angular velocity vector.
So this inertia tensor is a 3x3 matrix containing 9 components. Let's look at the physical meaning of these numbers because I think it helps ground the math. On the main diagonal, you have the moments of inertia, Ixx, Iy, and Iz.
Those dictate the resistance to rotation directly around the principal coordinate axis.
How hard it is to spin around x, y, or z.
Exactly. And they're calculated by summing the mass of every particle multiplied by the square of its perpendicular distance from the axis.
But it's the off-diagonal terms that I find really fascinating, the products of inertia.
Ixc, Iisc.
Right. The text notes they carry a negative sign in their summation, like negative sum of mi times xi times yi. What do these off-diagonal terms actually represent physically?
They represent asymmetry. They measure the dynamic imbalance of a spinning object.
Imbalance.
Yeah. Think about it. If you spin a perfectly uniform sphere around its center, the mass is symmetrically distributed across all planes. The products of inertia perfectly cancel each other out to 0.
So the tensor becomes completely diagonal.
Exactly. But if you have a lopsided mass like, say, a car tire that has worn unevenly, those products of inertia are non-zero.
Ah. And a non-zero product of inertia means that when you apply a rotation around the x-axis, the asymmetry generates a rogue torque around the y and z-axis.
Right. And the tire starts to wobble violently at high speeds.
Wait, so when I take my car to the mechanic for a tire balancing and they clip those little lead weights onto the rim,
Yes.
what they're actually doing is performing physical tensor calculus.
They literally are. They are adding precise point masses to force the off-diagonal products of inertia back to absolute 0.
That is mind-blowing. They are diagonalizing the inertia tensor of my wheel.
That is exactly what dynamic balancing is. Now, to make calculating these tensors easier for complex shapes, the text introduces something called the generalized parallel axis theorem.
I naught equals IC plus m times the quantity r squared times the identity matrix minus the dyadic RR.
That's the one.
Let's break down that equation because it's incredibly useful. Let's say you have a robotic arm holding a heavy payload. You already know the inertia tensor of that payload around its own center of mass. That's IIC.
But the shoulder joint of the robotic arm is rotating the payload from, say, 2 meters away. The pivot point has moved.
Normally, you'd have to recalculate the entire 9-component integral from scratch, which is brutal.
It takes way too much time. But the parallel axis theorem acts as a mathematical patch.
A patch.
Yeah, you take your original center of mass tensor, IC, and you just add a penalty term.
Oh, I love that. A penalty for moving the pivot. And that penalty term, m times the quantity r squared identity minus rr, is a tensor itself.
Right. It uses the total mass m, the distance vector r between the two pivot points, and the identity matrix I.
And that dyadic RR captures the exact directional penalty of the offset.
It is brilliant optimization. And because the inertia tensor captures all of this complexity into one neat package, calculating the kinetic energy of a wildly tumbling satellite becomes incredibly simple.
T equals 1/2 omega dot im dot omega.
The tensor absorbs all the chaotic geometry.
It does. It really does. But as we discussed with the Swiss cheese earlier, tensors don't just handle spinning mass. They handle internal destructive forces.
Which brings us to the core of mechanical and civil engineering, the Cauchy stress tensor and the hunt for principal stresses.
Right, because when you load a steel beam with weight, you generate a 3D stress state inside the material.
And the text visualizes this by pulling an infinitesimally small cube of material out of the solid.
Just a microscopic little cube. And on each face of this cube, you have stress components.
You have the normal stresses sigma x, sigma e, sigma z, which act exactly perpendicular to the faces.
So this is pure tension or compression. It's either ripping the cube apart or crushing it inward.
Exactly. And then you have the shear stresses tau c, tau z, and so on, which act parallel to the faces.
These forces are trying to slide the faces of the cube past each other, like rubbing your hands together.
Right. Now, a critical physical limitation is applied here. For the material to be in static equilibrium, meaning the steel beam isn't magically spinning in place, the sum of the moments around the center of our microscopic cube must be 0.
Because if it wasn't 0, the cube would be rotating.
Exactly. And this equilibrium requirement forces the stress tensor to be symmetric.
So tau c must equal tau x.
Right. The shear force trying to slide the top face to the right must be perfectly opposed by the shear force trying to slide the right face upward. Because of this symmetry, our 9-component tensor only actually has 6 independent variables.
Okay, so we have our stress matrix. But an engineer designing a bridge doesn't just want a matrix.
No, they don't care about the matrix itself.
Right, they want to know one thing. At what exact point and at what exact angle is this steel going to snap?
They need to find the principal stresses.
And to find them, the text uses a brilliant geometric derivation. It actually slices off a corner of our stress cube with an inclined plane, creating a tetrahedron.
A little pyramid. 3 faces are perfectly aligned with our original x, y, and z axes, but the 4th face, the sliced face, is defined by a normal vector n.
So we set up the force balance equations on this tetrahedron, and then we take the limit as the distance to this inclined plane, h approaches 0. We shrink the pyramid down to a single mathematical point.
And then we apply the ultimate condition. We ask the math, is there a specific orientation, a specific angle for this inclined plane, where the shear stress completely vanishes to 0?
We set the shear components to 0, and the balance equations simplify into a classic eigenvalue problem. Though the text frames it algebraically as finding the roots of the characteristic equation. All right, let's dig into this because this isn't just the magic of algebra. Setting the shear stress to 0 isn't some arbitrary trick.
No, it has massive physical meaning.
If the shear stress is 0 on a specific plane, it means 100% of the internal force vector on that plane is acting perpendicular to the surface. It is pure normal stress.
Exactly. And mathematically, a plane with 0 shear stress must be the plane experiencing the absolute maximum or minimum normal stress in the entire material.
That maximum normal stress is the principal stress, sigma n. It is the absolute limit of what the material is feeling.
To solve for sigma n, the text expands the determinant of the balance equations, which gives us a cubic polynomial. Sigma n cubed minus I1 sigma n squared plus I2 sigma n minus I3 equals 0.
And here we see our tensor invariance again. The coefficients I1, I2, and I3 are calculated directly from our original stress matrix.
They are.
Explain to me how these invariants connect back to the physical reality of the steel beam. Because it's not just algebra.
Not at all. Let's look at the first invariant, I1. It is simply the sum of the normal stresses. Sigma x plus sigma e plus z.
Which is the trace of the tensor.
Exactly. Physically, I1 relates directly to the volumetric stress. It describes how much the material is expanding or compressing in volume, totally independent of how it's changing shape.
Oh, because volumetric expansion doesn't care about your coordinate axis.
Exactly. So I1 is invariant. It is a fundamental truth of the stress state.
So the math forces these invariant physical truths into a cubic equation. And because it's cubic, when you solve it, you get 3 roots.
And those 3 roots are your 3 principal stresses.
Example 6.3 in the text gives us a concrete look at this. We are given a symmetric stress matrix with normal stresses of 7, 6, and 5 megapascals and some shear stresses of -2 and 2.
So you calculate the invariants, plug them into the characteristic equation, and you get sigma n cubed minus 18 sigma squared plus 99 sigma n minus 162 equals 0.
And when you factor that polynomial, you find the 3 roots, 3, 6, and 9 megapascals.
Right, and that 9 MPa, that is your major principal stress. It is the absolute maximum tensile force tearing at the material. 3 MPa is your minor principal stress.
And once you have these roots, you can plug them back into the direction cosine equations to find the exact angles, the principal axes, where these extreme stresses occur.
And if that 9 MPa exceeds the yield strength of the steel grade you selected for your bridge fails.
It's that simple. The tensor mathematics flawlessly predict structural failure limits.
They really do.
But solids are relatively predictable. I mean, they hold their shape. What happens when we apply tensor mechanics to something that flows?
Fluids. The text transitions into the stress state of Newtonian fluids. And the really cool thing is the tensor framework holds up beautifully, but the physical inputs change.
So to define a Newtonian fluid, the text gives us 3 postulates. First, the stress tensor is a linear function of the rate of strain.
Meaning the stress depends on how fast the fluid is deforming, not how far it has deformed.
Right. Think of water. You can push your hand through it slowly with almost no resistance. But if you slap the surface of the water at high speed, the strain rate is incredibly high, and the fluid pushes back with immense stress. It feels like concrete.
Exactly. Second postulate. The fluid is isotropic. Its properties are uniform in all directions.
And third, when the fluid is perfectly at rest, the only stress inside it is thermodynamic hydrostatic pressure, which acts equally in all normal directions.
Based on these postulates, the text derives the viscous stress tensor, and this derivation introduces a fascinating distinction between 2 types of viscosity.
This stood out to me too. So the equation requires a coefficient mu, which is our standard shear viscosity.
This is what we intuitively understand, right? Honey has a high mu, water has a low mu. It's the resistance to layers of fluid sliding past each other.
But there's a second coefficient in the equation.
Yes.
Take K, the coefficient of bulk viscosity.
Yes.
And the text links this directly to a term involving the divergence of the velocity field, nabla.v. What exactly is bulk viscosity measuring?
So bulk viscosity K measures the fluid's resistance to rapid, uniform changes in volume. The divergence of velocity, mathematically, is the rate of volumetric expansion.
Okay, so how fast it's compressing or expanding.
Right. Now, in many standard engineering problems, like water flowing through standard municipal pipes, we treat the fluid as incompressible. The volume doesn't change, so the divergence is 0. And that entire bulk viscosity term simply drops out of the Navier-Stokes equations.
It just disappears. But when does it matter?
Oh, it matters in extreme high-speed fluid dynamics.
Like what?
If you are designing the nose cone of a hypersonic missile, or if you're studying the propagation of shock waves through the atmosphere, in those cases, the air is compressing violently. The rate of volumetric change is massive. In those scenarios, the bulk viscosity K becomes a dominant source of internal stress and energy dissipation in the fluid.
It is stunning to me that the exact same rank 2 tensor framework scales from the crushing point of a static steel beam all the way up to the aerodynamics of a hypersonic missile. It is a universal language.
It truly is.
But as powerful as all this math is, the author of the text saved the most elegant, almost magical shortcut for the very last section.
Oh, yes. We are talking about Euler's theorem and the J.W. Gibbs rotation operator.
Yes. Introduced around 1901. So up until this point in the deep dive, if we wanted to track a complex object tumbling through space, we used Euler angles. We chained together multiple 3x3 matrices. R 3 times R 2 times R1.
Which, as we established with the Apollo 11 gimbal lock and the non-commutative nature of matrices, is computationally heavy, it's prone to singularities, and it's conceptually messy.
But Euler's theorem proves an absolutely wild geometric truth. It states that the most general displacement of a rigid body with one fixed point can be achieved by a single rotation about a single perfectly aligned axis.
Let that sink in for a second. It does not matter if a satellite tumbles through 15 different chaotic rotations on 15 different axes. The total net change in its orientation from start to finish can always be perfectly replicated by rotating it just once by a specific angle beta around one specific vector axis n.
It is the ultimate mathematical optimization. It's like discovering a secret tunnel in a video game that lets you skip the entire level. You just bypass the maze.
That is a great way to put it. And J.W. Gibbs formalized this into a single operator equation. R as a function of n and beta equals 1 minus cosine beta times the dyadic n plus cosine beta times the identity matrix I plus sine beta times the cross product of n and I.
Okay, let's break down the physical geometry of Gibbs's equation because it's brilliantly constructed. It takes any vector and rotates it around the axis n, and the equation has three distinct terms.
Right. The first term, 1 minus cosine beta times nn, uses that dyadic, nn, to project the vector onto the axis of rotation, because the component of the vector that is parallel to the axis doesn't change during a spin.
Right. If you spin a pencil along its length, the length doesn't move. Then the second term, cosine beta times I, scales the component of the vector that is perpendicular to the axis.
And the third term, sine beta times n cross I, uses a cross product to physically swing that perpendicular component through the angle beta in the plane of rotation.
It perfectly deconstructs the vector, spins the parts that need spinning, and pieces it back together.
It does. Let's prove just how much time this saves using example 6.4 from the text, because I think it makes it so clear.
This example blew my mind. Okay, so we have a physical slab, let's say a smartphone, sitting vertically on a table. We are going to apply two separate 90-degree rotations. First, we rotate the slab 90 degrees around the original x-axis, so it falls flat on its back.
Right. So the initial normal vector of the slab face is pointing in the y direction, vector j. After the first 90-degree roll about the x-axis, the normal vector points straight up in the z direction, vector k.
Then we apply the second rotation, 90 degrees around the new y prime axis.
And after this complex two-step maneuver across moving axes, the final normal vector ends up pointing in the ER direction again, though the slab itself has totally changed its overall footprint. Tracking this with standard Euler matrices takes multiple steps.
But the text uses Gibbs's operator to skip the sequence. It calculates the equivalent single axis of rotation, n1, and the single equivalent angle, beta 1. And the angle it reveals is exactly 120 degrees.
Yes. The text proves mathematically that those two separate 90-degree orthogonal rotations yield the exact same physical displacement as spinning the slab 120 degrees around a diagonal axis, defined by the vector I plus j plus k over the square root of 3.
One spin, 120 degrees, and you arrive at the exact same final state. The implications of this for modern computing are staggering.
Oh, absolutely.
If you are coding the physics engine for a video game in Unreal Engine and you have a character tumbling down a flight of stairs, you cannot afford to calculate 3 matrix multiplications for every single polygon, for every single frame of animation. The processor would melt.
Exactly. Modern computer graphics, robotic arm kinematics, and missile interceptor guidance systems rely heavily on this logic. By using axis angle representations, which evolved directly from Gibbs' operator into modern quaternions computers, calculate the single direct path from orientation A to orientation B in a fraction of a millisecond.
It's taking the scenic complex route through a 3D matrix and replacing it with a straight line. Gibbs literally gave us a cheat code for reality.
He really did.
Well, we have covered an immense amount of ground today, pulling back the curtain on the mathematics of the physical world.
We started with the geometry of shifting perspectives, exploring how the Kronecker delta and orthogonality give us the transpose shortcut for rotation matrices.
We tracked unconstrained motion with Euler angles, dissecting the non-commutative sequence that caused gimbal lock in the Apollo missions.
We expanded into Cartesian tensors, seeing how contraction and the Einstein summation convention reduce the massive dimensionality of a system into its core invariant truths.
We used the inertia tensor and the parallel axis theorem to perfectly capture the dynamic wobbles of rotational mass. We sliced the Cauchy stress block into a tetrahedron, hunting down the principal roots of the characteristic equation to find the exact breaking point of a steel beam.
And we scaled those exact same tensors to understand bulk viscosity in supersonic fluid dynamics.
And finally, we used Gibbs's rotation operator to bypass the chaos of matrix sequences, proving that any complex 3D tumble can be distilled into a single elegant spin.
It is a remarkable testament to the universality of mathematics.
It really is. So, for you listening, the next time you see a passenger jet banking through the clouds or an industrial robotic arm swinging into place on an assembly line or even just a heavy truck driving over a suspension bridge, Remember, the tensors, the invariants, and the direction cosines, this invisible, perfectly balanced mathematical scaffolding is executing silently in the background, holding our entire physical universe together.
And that actually leaves me with a final thought for you to mull over. If the exact same rank 2 tensor mathematics govern both the internal crushing stresses of a stationary steel bridge and the wild rotational dynamics of a spacecraft floating in a vacuum, could be that the fundamental nature of our physical universe is less about the objects themselves and entirely about the underlying geometries and transformations that connect them.
Now, there is a question to keep you awake tonight. Thank you so much for joining us on this deep dive into the invisible mechanics of reality. Stay curious, keep exploring, and we'll catch you on the next one.